Welcome back, students. This is the beginning of a new section covering some models that are more complex than linear regression. And in order to get estimates of our beta coefficients in these more complex nonlinear models, we use a method called maximum likelihood estimation. And the mathematics behind maximum likelihood estimation can be really complex. I'm not going to go over all of that. I don't even understand it myself. But I think I can give you a pretty good conceptual understanding of what this is all about. In order to do maximum likelihood estimation, we need a likelihood function. And a likelihood function is one that produces the likelihood of a set of beta coefficients given your data set. And so mathematically, this looks kind of like this, where this theta is the vector of beta coefficients that you're estimating, and x is our matrix of data. And so this left part of the equation can be read as the likelihood of theta given your data. So it's always conditional on the data that you have, because the beta coefficients are estimated from your data, so they're always conditional on the data that you have available. And then that's equal to some function of your vector of beta coefficients and your data. So the x is your data, that is what it is, and theta, this vector of beta coefficients, are an estimate of the beta coefficient. So you can guess what you think the beta coefficients are, plug them in there, and you'll get some likelihood. Then you can guess another set of beta coefficients, plug them in, you'll get another likelihood. The one that has the highest likelihood will be the best set of beta coefficients, and you can keep doing that. And the goal is to find the set of beta coefficients that maximizes the likelihood function. And these then become your parameter estimate. Now, in the case of linear regression, it can be shown that when the assumptions of linear regression are met, that the ordinary least squares estimates are the maximum likelihood estimates. But because linear math is much easier than nonlinear math, there's a closed form solution for the ordinary least squares estimate. We can just take our data, our matrix of explanatory variables, and our vector of response variables, and plug them into an equation and calculate the ordinary least squares estimates directly. And so that's really handy. With nonlinear relationships, however, the parameters have to be searched for through a process known as optimization. There's no closed form solution. There's no way that we can just calculate these directly from the data. So to help us think about this conceptually, consider a maximum likelihood estimate with a single parameter. We'll call that single parameter beta. And so that's going to be the slope of a line with no y-intercept, so it's going to force it to go through 0, 0, through the origin. And in this case, this is just a linear model, and with linear regression, the value that we're trying to minimize is the sum of squared errors. And again, with linear regression, we could just calculate our slope directly, but suppose we don't know that, and we want to guess at what the slope is, and so we start with a guess of, say, -2, and that produces a sum squared error, looks like about 18. We don't know if that's good or bad, so we try another guess. We say -3, and when we plug -3 into this equation and compare it with our data, it gives us a sum squared error of about 26. That's worse than 18. And so we know we're going in the wrong direction, so we try -1. We plug the slope of -1 in here, and that gives us an estimate of, looks like about 12. That's better, so now at least we know we're going in the right direction. We can try 0. We're still getting a lower sum square error. That's good. So we'll go with +1. That's still an improvement. We can try 2. It's still better. So we keep going. We'll try 3. And 3 gives us a worse sum of square errors. So we want to go back to 2. Maybe we try 2.5 and then 1.5. And eventually we end up concluding that the slope that minimizes the sum of square errors is 2. So that's the basic process of optimization. And the field of optimization is a huge field in mathematics. There's a lot of different methods, and that's going to become clear to us as we continue with some of these nonlinear types of models. For instance, if we have a likelihood function that looks something like this, and it's well formed mathematically, one thing we could do is take the derivative of that function. Remember, the derivative shows us the rate of change, and the rate of change is basically the slope, right? And so we can calculate the derivative at 2 and see that it looks something like this, and we can use that derivative to point us in the right direction. So we'll go down in the steepest direction. That's coming down here, and the steeper the gradient, the bigger the guess we can afford to make. So we can start with -2. We know we need to go up, and maybe we go to 0, and now the slope is starting to flatten out a little bit. So maybe we take not quite so big of a guess next time, and we just go by 1, and it's flattening out more. And so the flatter the slope, the smaller the guess we make to the next. And eventually we'll get to this spot here where the derivative is 0, where the slope is 0. And that's going to be our minimum. We don't even have to go up and come back and forth until we narrow down on something. Once we get to the point where the slope is 0, then that's our minimum. And so again, if the function is well formed mathematically so that we can calculate derivatives, we can go through this process that's known as gradient descent to arrive at our estimate with fewer guesses. Each guess in this optimization procedure is an iteration, so it's an iterative process of finding, in this case, the minimum, but eventually we converge on a single point, and that becomes our parameter estimate. Now let's go to Jupyter Notebooks, and we'll see how we can a conceptual understanding of this. So I already have my notebook environment up and running. I'm going to open exercise number 15, maximum likelihood estimation in concept. And let's start by simulating some linear data with a slope of 2 and no y-intercept. So we're just going to have our beta 1 coefficient equal to 2. We'll start with our random seed of 2021. We'll create an array of random integers from 1 to 100. And we'll create 200 of these. And then we'll create some normally distributed error terms, and we'll calculate our response variable y, again as a slope of 2, our beta 1, times our x variable, plus this error term. This is just like we've done before, nothing terribly different. And then we'll convert these 3 arrays into a pandas data frame. And so when I execute this code block, we end up with a pandas data frame like this. If we plot the data out, we get something that looks like this. It looks like a line that's fit would go right through the origin 0, 0. That's good. That's the model that we've created. And you could probably look at this and see that it has a slope of 2, but this is very simple data. Assume that we didn't have the ability to plot it out and had no idea where to start guessing what the underlying slope is. Let's start with trying a slope of -1. So I'm going to plug this -1 in here, multiply it by our x column, and that will create a new column called y hat. And then we'll print out the mean squared error, which we can do just with our scikit-learn mean squared error metric, because all we need for that is a vector of observed data and a vector of predicted data. And then we'll also plot out the same plot, but with what our prediction line looks like. And so with a slope of -1, our prediction line looks like this. As you might guess, our mean squared error is large, almost 30,000. So that's probably not good, but let's try a slope of -2, see if that's any better. And that's worse. Our mean squared error now is almost 53,000. So we're going the wrong direction. We'll try 0. That's an improvement. This is our prediction line with a slope of 0. We can try a slope of +1, and that's even better yet. And we can see this is getting to be a much better fit now. We'll try with a slope of 2, And that looks really good, actually. But again, suppose we didn't have the ability to plot this out. All we had to go on was these mean squared errors. And so let's try +3, and now we're getting worse. So we go back and we try 2.5. That's better. Maybe we try 2.1. That's even better. So it's starting to look like 2 was our best. Let's try 1.9. And that's worse again. So what we're doing is we're converging in on the value of 2 as the best estimate of our slope. So again, that's this iterative process. We went through, 8 or 9 iterations to find the best slope, and we eventually converged on the value of 2. So let's plot out what a likelihood function in this case might look like. I'm going to create an array of slope values that go from -1 to 5 with a step of 0.5. So we go -1, -0.5, 0, 0.51, etc. And then for each slope, we're going to calculate a mean squared error and put that in array as well. So I'm going to start by creating an empty Python list called MSE, and then we'll loop through all the slope in our slopes array, and for each slope we'll estimate our predicted values, and then we're going to append this mean squared error to our MSE list, and then we'll print out that list. And so for each slope in our slopes array, we have a corresponding mean square error in our mean square error list. And so we'll create a new pandas data frame called estimation, and this is just going to have 2 columns in it. One's going to be slopes and one's going to be a mean squared error. And when we do that, it looks like this. And if we plot that out, it looks just like this. And so again, the goal is to find the estimate of the slope that best fits the data. And we've seen a couple different ways we can do this. One is just by starting to guess a slope and trying to move in the direction of the lowest mean squared error until a slope starts increasing and going back and eventually converging on 2. That's one method of optimization. The other method we talked about, gradient descent, where we can compute the derivative of this function, and we can use the derivatives to come down and converge on 2, probably in a fewer number of steps, because we're wise enough to know which direction we're going and to change our guesses by a smaller and smaller amount as the derivative approaches 0. And when it gets to 0, we'll know we're at the minimum. And so that's an increase in efficiency over this kind of iterative guessing process, but it's still an iterative process. So the take-home message is that we're finding the slope that minimizes this function. There are a number of different optimization methods that we can use to do that. This is a very simple example, so it probably doesn't matter which optimization method we use. We'll arrive at 2 relatively quickly. But in some more complicated examples, certain optimization methods might be a lot more efficient than others, but may end up with some problems of their own. And so we do have to think about things like the method that we're using that's going to come into play in the future. As we go through this course, we'll see we have the option of choosing different methods for solving these optimization problems. Now, I said that with maximum likelihood estimation, we're trying to maximize a likelihood function. And here, we've been minimizing our mean squared error, but really we could just look at the negative mean squared error. And so I'll do that. I'll actually create a variable called negative mean squared error, and we'll plot out the slope against the negative mean squared error. And that just flips this likelihood function upside down, and now we have a function that we're trying to maximize to find the slope. But everything else that we've discussed doesn't change. We have a number of different methods. We can just keep chasing the highest negative mean squared error, or we could do a gradient ascent till we get to where the derivative of this function equals 0, and that's going to be our estimate. So you can look at this as either a maximization problem or a minimization problem. It's really the same thing. With maximum likelihood estimation, we talk about maximums because we're trying to maximize a conceptual value. It's the likelihood that our parameter estimates are the best, but really there's no difference conceptually. In linear regression, we talk about minimizing the sum squared errors, which is almost the same as the mean squared error. Just the mean squared error is the average, not the total sum. So hopefully that helps conceptually to understand what's going on. So this is an example in one dimension where we only have one beta coefficient to estimate. We can easily visualize what this might look like with two parameters. So in this case, we have our x and our y-axis. Each one represents a beta coefficient, and we're trying to find the combination of this beta coefficient that minimizes this function, or if we flip it over, to maximize this function. You can imagine with this method it gets a little bit more complicated as far as guessing our parameter estimates and trying to find some guesses that will converge on the best estimate. This is where you can see a method like gradient descent would really be advantageous. So say if you start here, you know automatically that you're going to go down the steepest gradient, and you'll continue down the steepest gradient until you get to the point where the gradient is 0. That's going to be the bottom of this concave surface, and that's going to give you your parameter estimates, the two parameters that minimize this surface function. Now, as always, if we add more than two parameters, we start getting into multidimensional space, which starts getting really, really difficult to visualize, impossible to visualize, in fact. But the concept is the same. We can perform gradient descents in hyperdimensional space just like we can in one or two dimensional space, and it'll get us to the same point. Now, in an ideal world, our likelihood function would be well formed mathematically like this one, where there's just a single low point that we can reach from any other point in the surface. In that case, optimization becomes relatively straightforward. However, that's not always the case. There are situations where our likelihood function can be more complex. In this case, it's really complex. And there can be things like a local minimum, when what we really want is the global minimum. We want the lowest point of this entire surface, which might be here. But say if we started with our guesses at right here and gradient descent took us down, we might end up in this local minimum, which is not the same as the global minimum. And so our parameter estimates here would be quite a bit different than the parameter estimates that gave us the global minimum. And so we might want to consider other optimization methods that will maybe at least try doing a gradient descent from a number of different points and finding out which one takes you to the lowest point or something like that. So conceptually, that's a way to think about it. Again, this concept of optimization is a huge field in mathematics. It's quite complex. We don't have to understand the math behind it, but we do have to understand at least a little bit conceptually what the process is. And so I just want to finish this lecture with some take-home messages about maximum likelihood estimation that are going to be relevant. Even if we don't have to worry about the math, there's still some concepts that are relevant. And so the first one is that these are really computer intensive. People had figured out the math behind linear regression many, many, many years ago, because again, linear mathematics are relatively simple. There's a closed form solution. You can plug your data into a formula and calculate your beta coefficients directly without having to go through this iterative process of finding the best set. That process that we've talked about, of this iterative process of finding the parameter estimates that maximize some function, you can imagine if you tried to work that out by hand, it could take you years and you still may never come up with the right answer. So while people have been doing linear regression for many decades, it's only been in the past 2 or 3 decades that we've had computers powerful enough to perform maximum likelihood estimation. And so it's only been in the past couple of decades where we've really had the ability to use some of these more complex nonlinear models like Poisson regression and logistic regression and some others. The second take-home message is that this process of optimization can be complex. There are different methods available. Each has advantages and disadvantages. So gradient descent works really well when you have a well-formed likelihood function that has just a single minimum, but in some other cases, we might want to consider some methods that are not susceptible to the trap of falling into local minimum and that will actually do a better job of finding the global minimum. And there's also some different terminology that comes into play when we're talking about maximum likelihood estimates. Things like iterations and solvers. So each solver would be a different approach to optimization. And again, there can be several of those. Things like convergence, we talk about converging onto the minimum. So sometimes when we're using techniques that use maximum likelihood, we'll get messages that say something like it failed to converge and you have to increase the number of iterations. We'll have parameters for these models that will determine the maximum number of iterations to perform and what solver or what optimization technique you want to use, and things like a tolerance value to reach convergence. So this is just some small number that you can specify that says, hey, when you get to this point, that's our parameter estimates. We don't got to look any further. And we'll also hear this term gradient descent thrown around. Again, that's one possible optimization method that works really well when you have just a single global minimum and no local minimum. We don't have to be experts in optimization to use statistical methods that rely on maximum likelihood estimates, but we do have to be at least conceptually aware of what some of these terms mean. That was my goal for this lecture. Hopefully I've succeeded. Hopefully you have a bit of an idea of what some of these things mean now, because we're going to see them quite a bit from here on out. So thanks for listening. In the next lecture, we're going to talk about scaling our data, and that involves modifying our data so all of our variables are on a similar scale. And that provides a lot of advantages, especially when we're talking about maximum likelihood estimates. So we'll talk about what some of those advantages and disadvantages are, some of the different methods for scaling, and we'll see how easy it is to do in Python with scikit-learn. And we'll see you then.